we need, okay, I'll try to make a picture there so you can look at it while I explain this, and the people from the stream, well, they should have come, I don't know. There wasn't any real way that I could solve this at home in a good way. So we have our Lagrangian picture, right? And this is a point this is an ill-defined point in our model. So it's exactly those points where, if we take a look at this curve, the projection onto this axis is orthogonal, well, is tangential to the curve itself. So these are the points that are critical. And this is the intuition that you have to keep in mind. So we've seen rho diverges if one of our eigenvalues fulfills this condition. This gives us, our first or primitive shell crossing condition. But in order to develop the complete set of conditions, we need to take a look at this geometry right there. So if we interpret R as a projection of that from that Lagrangian submanifold onto the base, and the base that I've called here B, it's just the values of that R can take. So in our case, it would be R3 or something like that. Then we see that we get a shell crossing condition if there is, if there is a vector, I mean, this is difficult to differentiate. Okay, so if we have a point in this big space for which we can find a vector on its tangential space such that that vector is orthogonal to the curve, then we've won. And this is exactly what happens here. So what I'm saying is the direction of the projection is given by some vector that goes down. Now, a way to parameterize this is to say, okay, so I want this to be orthogonal to the gradient of my curve. So that's what we say if we find a vector Vt such that this is fulfilled, then we're done. The problem is that because we're working on more bigger spaces than what this image is suggesting, I have to go to the big tangential space. But in essence, the only thing I'm asking is that I want a non-trivial vector to exist such that this happens. And this would be the point Bs. If we then, we've seen this can be diagonalized, then this matrix equation breaks down into, if we take the dimension to be L, usually it's 3, then we get L different equations for eigenvectors and eigenvalues. And then we say we need for some vector from that tangential space, we need that all of these equations turn to 0. So that's a difference between the complete shell crossing condition and the primitive one that we saw. In the first one that we saw, it was alluded to that it's enough to ask for one of these equations to maybe vanish, because one could think, well, if one of my eigenvalues is equal to -1, then the thing diverges anyways. But actually, for a real shell crossing to occur, we need for all of the eigenvalues to this, we need that this equation holds for all of the eigenvalues. And indeed, for this, we don't need this to vanish. We will see that for a caustic to occur, it has to happen for at least 1, because otherwise this vector cannot be non-trivial. But yeah, essentially, this is a general shell crossing condition. And because we have a trivial way and a non-trivial way, to say it in some way, for this equation to be fulfilled, this is the way we will start categorizing our caustics. This is the theorem expressed in a more, mathematical way. for which you need transversality. I don't know how, well, how sensible it is to go into this now, but essentially it says we need this condition to hold for all of the eigenvectors and eigenvalues. So yeah, as I said before, we have seen, okay, so now we have developed, we have established that one of the main criteria that we can use to find our caustics are the number of eigenvalues n that fulfill the shell crossing condition in a trivial manner, namely by reaching the value -1. If it's fulfilled for no eigenvalue, then we have no caustic. That is something that one has to prove, because essentially, I mean, this equation could be fulfilled without, I mean, we could say, well, but this doesn't have to be 0 for it to be 0 for all i's. But if this is the case, since all eigenvectors form a basis of their respective vector space, if for all eigenvectors Vt is orthogonal to them, then Vt has to be 0. And this is something that we exclude by saying that Vt has to be non-trivial. So if this is the case, we have a non-caustic. If only one is -1 equals -1, then we have a caustic of class ak. And if we have two eigenvalues fulfilling this, then we have a caustic of case dk. And ak, but ak are only relevant, like, I think at dimension 6 or 7. So it's something that for our space, not even our space-time. So this is something that is not relevant in normal hydrodynamic models. One can show that if more eigenvalues than that are 0, that the models this would correspond to do not fulfill certain stability conditions that we want for generic spacetimes to be fulfilled. So that would mean that the spacetime that would fulfill that could be infinitesimally perturbed, and then you would fall back into one of the generic cases, which is, at least in my opinion, a criterion for non-physicality, because, I mean, we assume that our space or space-time or reality is more or less stable in a sense. Yes. The subscript k there represents the codimension in space-time of these classes, because depending on how many additional conditions we impose, the spaces or the dimension of the caustic spaces they describe is going to be smaller and smaller. So yeah. And the criteria for the subclasses K are going to be discussed next, and they will describe how the caustic conditions are exactly met. So we are going to start first with the classes AK, and the first class AK, namely the class A2, which has codimension 1, gets fulfilled automatically if for that point, for some eigenvalue, that condition is fulfilled. And we don't impose any additional criteria. So since we're only imposing one criterion, we only lose one dimension, to say it like that. If you're familiar with the Sildovich model, those are the points that describe the boundaries of the Sildovich pancakes. So these would be the edges of different streamed regions where nothing else happens. If we take that condition and additionally say, well, I don't only want this to be fulfilled, I also want I also want the sort of transversality or tangential condition to be fulfilled. So I want the gradient or the direction in which the eigenvalue changes. Yeah, I don't know, guys. Like, do you think it's sensible to go over this? Because it's really technical and I don't really have pictures. I don't think this is really productive. What do you think? Because I mean, it's really dry. I mean, I can show you. Okay, but I don't know if we can relate this then to the equations. Yeah, that's correct, yes. Okay, so we will do that. But I think for that I need to make some sketches at least. Okay, so I'm going to do this for the K2 and the K3s because I think they're the most important ones. K4 and K5, I mean, K5 you can't even draw because it has codimension 4, so it only exists in spacetime. So I cannot draw that. And K4, I have a picture for that right here. So I think that would be fine. So I'll try to do it 3D. This is our spacetime. And then there are some structures emerging, or we see some structure emerge at some time. For instance, here. This would be, I'll draw the whole structure, and it's fine. Yeah. So this Sedlovich approximation tells me that matter condenses in sort of pancake-like structures. These structures have a boundary. This boundary is a caustic of class A2. But these structures can merge, they can disappear, and they can appear. And also these structures are not round pancakes, but they're sort of like saucers, so they go like this. So they are not really smooth at the edges. This is important because these points here, where they're not really smooth, these are points of class A3. And they determine the regions where I get new structures. So if I were to look at my hydrodynamic model and I would want to know, okay, where are new structures emerging, I would start by looking at these points here. For instance, we can have another structure here. And with time, these ones grow. So after some time t that passes, they meet up. And they form a big structure. This point here would be part of this yellow line because they're meeting up at the yellow line. But this point here wouldn't only be a normal A3 point. I mean, to begin with, A3 singularities says, I mean, also suggested by the index here, they have codimension too. So if we're in 3D space, they are lines. The meetup points are not lines, they're points. This point right here is special. I think in my thesis, it's called A3 plus or minus. I don't know which one, it depends on the orientation of some equation. But anyways, these are points of this class where the tangentiality condition I showed before. So we had something like the condition for A3, and A2 had the following condition. Mu I plus 1 is 0 for I and for some I. The A3 condition was this one, but additionally that there is a vector that if labeled like this, but it's not squared, it's just, this is a label. It's a sort of, tangentiality condition, and it comes from the fact that at these points, the eigenvalue, the direction in which the eigenvalue changes is parallel to the direction in which the pancake is evolving. So this and the direction in which the eigenvalue changes is orthogonal. This is what this condition says. But this can be fulfilled again in two ways. Either it's complex, so either we have something like my pancake is moving forward, and this is the edge of the pancake, so we have a normal orthogonality condition, or we say that this vector here is trivial again, as we did before. So we make a distinction between when the conditions are fulfilled trivially and when they are fulfilled more in a more geometric sense. If this condition is fulfilled trivially, then we have a maximum, a minimal, or a saddle point in our eigenvalue field. And these are the points A3 plus minus or plus minus. Depending on how big your dimension is, you have different kinds of points of this sort. And these maxima and minima correspond to points where structures emerge, merge, or vanish. So this is a bit the intuition behind the categorization. This can be rinsed and repeat. So in the case A4, I say, well, I want this condition to be fulfilled, I want this condition to be fulfilled, but additionally, I want, again, my eigenvector Vi to be orthogonal to the, let's do it like, yeah. And mu II is exactly this. So because at the normal edges, this is not trivial, I can take a derivative again, and I can ask, okay, when is this now additionally not only orthogonal to the direction in which my pancake is moving, but when is it orthogonal to the eigenvector field? This is a bit weird in 2D and 3D because you don't have enough vectors to do this, but if you have bigger spaces, then, well, you can be orthogonal to a lot of things at once without them being parallel. So, and for the A5 condition, we again ask for some vector T4 to be orthogonal to this. Hello. So in the end, what we're doing is we are forcing our system to be orthogonal to more and more and more fields until our dimensionality tells us there are no more fields that you can ask this to be orthogonal, like stop. Yeah, so I mean, this you can imagine. For the A4 condition, it's a bit more complicated, I feel like. I can try to draw it a bit better. So, but for this, we would need to assume that we're already, I mean, we have to zoom in on this. So I'm going to zoom in on this. And we're going to imagine that we are in that this sheet right here is already so we are already on our pancake. Then this is the contour, the edge of the pancake in some sort. They come together. This is A3. And now we say, and this you can see right here, the difference to that case is that here, not only do we have, because I mean, you have to think about this is then also parallel to the direction in which the pancake is expanding. This point is also, since we are on the sheet already, we are also fulfilling the condition for this to be parallel to the sheet itself. Do you know what I mean? I don't know if I can draw it in a better way. So, I mean, yeah. The thing is, I can separate them too. Maybe that's easier. So you have these points here. So you have points like these ones where you're at the edge. But at these points, you're not only at the edge of the pancake, but you're also collinear to the pancake itself. So that's why these points are not the same ones as any other point of this edge. Because we are on the sheet. We're not only in the whole of the space, but we're on the sheet. And these points here are A4 points. And when two A4 points merge, we get a special A4 minus or plus point, because that means that this condition then is fulfilled trivially again. So in the upper picture, the pancake is this structure. Yeah, of this kind of, yeah. And what I did now is I zoomed in, I assumed we were already, I mean, it's not this picture, this is another picture. The zoom in thing is a bit misleading. But we assume now that we're already on a pancake structure where we have two edges that come together. Which, I mean, if you take a look at this, it can't happen. But there are more complex pancake structures where this can happen. Where you have like you have a big sheet, and then on the sheet you have like these edges, and they come closer together. And then because you are collinear to the sheet, or if you're collinear to the sheet, then you get this special condition A4. And more multi from not so multi-stream regions, yes. That's exactly what the pancake does, yeah. So the moment you cross a pancake region, then you get up, you lose or you win two streams, essentially. Yeah. So is this picture maybe clearer now with the sketches and the person doesn't look that content? So yeah, it's a bit technical. Yeah. Sorry, no, continue. I don't want to interrupt. All right.
I remember from the last talk, like visualization was like how to like fold with a sheet of paper.
Yeah. I'm going to do it there because otherwise in the stream you won't see it. So the way this relates is the following. The problem is it's very hard to relate it because for me to be able to draw my pancakes, I need 3D. For me to be able to draw my sheet of paper, I need 1 or 2 because the face space isn't big enough. But essentially, it relates to this multi-stream region. So these are the boundaries. Here I have single stream. Inside of here, I have multi-stream, so something like 3 stream. These points here that mark the start and the end of this region, these are the A2 points. The problem is these are not A2 points because what I'm drawing here, this is a phase space. Like this here is L times BL in some sense, and this is L. So it's a bit problematic to compare them both. But in essence, this boundary here is A2. So when you go from points that are here, so where I can say, okay, this only relates to 1 point, as in comparison to here, where 1, 2, 3, my R relates to 3 different x's. This is the relation. The A3 points are points where this happens, or not the A3 points, but the A3 plus points are would be this point. So this would be an A3 point, because here a region like that is created. This would be an A3 plus point probably. Yeah. And more I cannot draw because this is too low dimensional for that. Mm-hmm. Yeah. 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 Exactly. What is a bit problematic about this picture is that because we're one-dimensional, because the thing is, okay, this is to be taken in a bit of quotation marks. This is one-dimensional, right? My Lagrangian manifold is one-dimensional, meaning the only caustics I can get are those that have codimension 1 max. The ones that have codimension 1 are the A2 points. So these points would be the edge of the saucer because the edge on a line are points. A3 only exists, A3 has codimension 2. So that means it only exists when I take a look at the Lagrangian submanifold times time. So this is the reason why I cannot draw an A3 point. The only way to show you the A3 point is to compare. Okay, the time is now in this direction, or no, it can also vanish. So the evolution from this to this to this needs an A3 point. But this A3 point only exists in space-time. That's not a space point only. So yeah, that would be the, does that help? Yeah.
The particular reason why the cost for like the boundary needs to be shaped like this? Like why does that have to be a concept? Why can't it be
something because well, I've been told that has physical reasons. If you're in the Sildovich model, then the collapse is anisotropic. And so you get like these sort of, like with time, when structures propagate, they sort of collapse into these oblong shapes instead of being like spheres. At least I think that's what yeah, Matthias does that. Perfect. That's what I read in Matthias' book. So yeah, no, I think, but that has physical reasons, not mathematical ones.
Okay, so in general, the cost you could have.
Yeah. Yeah. In general, what matters to me, and you will see that in the later part, is that you essentially take a look at Jacobians, take a look at how they lose ranks, and yeah, essentially you do that. And then according to that, you derive different types of normal forms. How that physically translates into a system, that's another question. And accordingly, you have to adjust the singularity theory you're employing for this to be, I mean, we'll see that later, but from vanilla singularity theory to get to a point where you can apply to Lagrangian structures, you have to take a lot of steps. And that mainly has to do with the physical framework you're working with. So, yeah. Yes. But yeah, so I think we can skip this because the D things are even, I can't draw those. So I think you can turn it on again. So these are the AK classes. Essentially, if you are if you have a three-dimensional space-time, you can also get singularities of type dk, d4 and d5. I won't go into them because they're like really cumbersome, which has to do with the fact that if you want two eigenvalues to simultaneously reach that condition, then you automatically fulfill the condition for these points to be also points of type A3 isolated from each other. So you get additional constraints that are not trivial to show. But yeah, they give rise to really interesting structures, I guess, but the details of that are not really important. And this is sort of an overview of all the caustics you can get in a three-dimensional fluid if you take time into account as a additional dimension. Yes. Density profiles, divergence density profiles have been derived for these singularities. What is interesting about that is, well, one has to be a bit cautious because these density profiles are mean density profiles. So what you take into account a region around the caustic and take a look at how it diverges polynomially. The problem is that in the Seldovich case or Seldovian case, the collapse or the divergences are really anisotropic. So taking a look at the mean density profile is a bit misleading. What we can see is a trend. So the more degenerate the singularity is, the steeper the divergence becomes. So that's something interesting. And it would be interesting also for future work to really take a look at how these profiles were derived, because with that can also be applied maybe to other models that are not hydrodynamical, for instance. Yes. And now I will waste a few words to, no, not waste, but I will quickly show you how this relates to a mathematical theory of singularities in order to like munch them both together. And then we have these beautiful pictures with pancakes and stuff, but we can additionally describe the behavior of the functions that describe those pancakes in a polynomial way by making a coordinate transform. So the concept of singularity theory, of general singularity theory, is the following. When we were, we all went to high school and did math in high school. And then there is a point where, well, we understand that there is something important about a derivative vanishing at a point. And there is even something more special about a derivative vanishing, or about multiple derivatives vanishing at one point at the same time. So singularity theory takes that idea and wants to apply it to more complicated functions, and not only for functions that are from R to R or whatever. So I take my function from Rm to Rn. You can expand this to manifolds by taking a look at charts, but this is not important here. And you take a look at the Jacobian, which is something like the derivative, the first derivative. And you say, okay, so I have a critical, in the one-dimensional case, I would have a critical point, and my first derivative vanishes. But for a matrix to vanish, you have to invest a lot of work. So you say, okay, so I don't want the whole thing to vanish. I just want the rank of my first derivative, so of my matrix, to be less than maximal. The case for the matrix to be 0 would be the case where the rank is the lowest it can get, namely 0. So we have a generalization there. And this is the first characteristic, or the first thing that defines singularity theory in comparison to Morse theory, which is the case where your functions are, well, you restrict yourself to functions from Rm to R. So you not only say first derivative has to vanish, you say, no, the rank has to be less than minimal. And then you can start by classifying on the basis of how many ranks you lose. So if you lose one rank, you have one type of critical point. If you lose 2, another type. If you lose 3, another type, and so on and so forth. Yeah. This gives you the so-called classes sigma I. I is the amount of rank you lose. And the cool thing about this procedure is that you can rinse and repeat. So then you take a look at the function, but you restrict it to a certain class. And then you take a look at the Jacobian there, and then you take a look at, okay, where does my Jacobian have critical points there? And then you can start adding indices to this. And this is exactly what the mathematician Boardman did. And this got him to the classes sigma I being a sort of indices group. The interesting thing about this is that this gives you a stratification of the source space of the function. A stratification is a patchwork of manifolds of a sort. So you don't have a manifold, but you have like manifolds sewn together in a nice way. And this is really nice because this allows you to sort of, if you imagine the source space of a function to be a chart and you don't know anything about it, it allows you to sort of delineate in which regions you have what critical points. And that, I think that's nice. It has some sort of aesthetic. And if it also has the structure of a manifold, then it tells you that you have a sort of structure and regularity behind critical points. It also tells you that if you deform functions in an infinitesimal way, that singularity structure is stable. And this is something I won't get into here, but a chunk of my thesis was to take a look at how stable are what singularities, because if you don't have, if the singularity structure of your functions is not stable, then you cannot do a coordinate transform to get a nicer function and hope for the singularities to still be the same. So we need them to be more or less stable in that sense. So yeah, as I said, if you know what Morse theory is, it's a generalization of Morse theory. Yeah, and therefore, for each type of these classes, we get a distinct polynomial. Maybe I should tell or try to motivate this a bit more, because I don't know, like the thing with the polynomial is pretty strong. The idea that Morse had when developing this theory was the following. When I have a function from R to R, well, this is full. Let me change the board. When I have a function like this, I'll take a look at polynomials. The first function that has a critical point is something that is quadratic. Fine. Then you know, well, you get this point, and then you know, okay, this can be described by a quadratic thing. Now I have another function, and this function looks like this. And then you might say, ooh, this critical point is different because here my first derivative is 0, but my second is 0 too. So I have a really distinct case here. And then, and the gist of Morse theory is to say, no, these cases are pathological actually, because when well, I can't, I'm too small for this. These cases are pathological because the moment I change these functions by a tiny little bit, this transforms into this. And here, this looks like this. This is quadratic in nature, this critical point right here. Because here my first derivative is 0, my second one isn't. So I have this behavior again. If I do the same, this I can do with this one too. Then I get 3 critical points, but they're all quadratic in nature. So what Morse said was, I have Morse functions. The thing is, Morse functions are general. They are defined on manifolds and stuff. But you say, there are kind of functions. They are called Morse functions. They only have Morse critical points, which essentially means their second derivative isn't 0. And they fulfill certain generality conditions in the sense that they are generic. There are a lot of functions that satisfy this. On the other hand, non-Morse functions are not generic because I can perturb them and then I get Morse functions again. What singularity theory does is to say, well, hold on. It's true, if you take a look at this function to be from a one-dimensional space to a one-dimensional space, then you're right. But if your function, if you not only take a look at these separate functions, but for instance say, okay, this is a family of functions where you have something like this. As a function. Then it's true if you interpret lambda to be an external parameter and not a variable, then it's true, then you can perturb these singularities away. But if you interpret lambda as being another variable, then within these families of functions, this singularity is stable. It has a lower dimension, but it's still stable. That's the generalization that singularity theory does in comparison to Morse theory. It allows for more parameters to become relevant. Yes. So for the talk to not be that long, I'll try to be a bit faster. This is messy. Okay. Well. Yeah. The only thing I will say regarding this is that what I've done here on this board is what we did in this slide was we took a look at functions and tried to classify functions with the help of their critical points. What we need for our physical theory, and that makes the adaptation a bit cumbersome or not that straightforward, is that in our physical case, we have a Lagrangian submanifold that is given by the gradient of a function s. The function s in literature it's usually called the generating or derivative function of a Lagrangian submanifold. That is the function used to define the Hamilton equations. So when you're in phase space, you usually say, well, the phase space is given by x, or q equals minus del h del p, and the other thing, that the Hamilton function is a generating function of the Lagrangian submanifold. So essentially, you have a function s that goes from R to 2L to R that defines the Lagrangian submanifold by telling you how you have to take derivatives in order for L of the variables to be constrained, and then you get your physical phase space or your constrained phase space. But as we have seen in that picture, it's not S that becomes singular. It's not the critical points of the function S that are problematic. It's the critical points, and we saw it here when we did the density. We're actually taking a look at the points where the derivative of R becomes 0. And R is itself the derivative of S. So our aim is to classify the different functions S, so the different Lagrangian submanifolds that get parameterized by S, by means of the critical points of its gradient and not its own critical points. So that's a bit nasty. Mathematically, what we're trying to do is classify functions of this form by means of the critical points of their gradients that have this form. So that's why I need, even though these functions are Morse functions, I need singularity theory to be able to categorize them in the way I want it. This classification is called in literature the ADE classification of singularities if we don't apply Lagrangian structure to it. Generally, the ADE classification of singularities amounts to 2 criteria. The first criterion is to take a look at the amount of rank lost of the Hessian matrix of S, which is nothing else than to take a look at how much rank my function R loses. So the same thing as a normal singularity theory. We see, if we take a look at the physical categorization that we did in the beginning, this is equivalent to the amount of eigenvalues that fulfill that condition. We saw it with the density thing, right? So the mu I plus 1 was the diagonalization of the Jacobian matrix of R. So this is an analogous distinction between the classes A and D of singularities that we saw in the physical case. That's nice. So it seems like we are doing something sensible here. The second criterion that the ADE classification of singularities uses is the multiplicity of the critical point. So how many further derivatives vanish, or in other words, the way it's actually defined mathematically, this, if I perturb this critical point, how many quadratic critical points do I get? In this case, the multiplicity would be 2. In this case, it would be 3. Depending on how many I get, this index becomes higher. So that's the second criterion. And this is equivalent to the conditions for the A mu classes that we established here. Namely, okay, I have this, then this vanishes too, this vanishes too, this vanishes too. So we develop more and more and more orthogonality conditions, and they are equivalent to these multiplicity, to expect the multiplicity to get higher and higher. For the decay classes, to show that the ADE classification gets more complicated for the decays, as does the case for the caustic conditions. So if you are interested in that, then I can give you sources for that, but I didn't prepare it for this presentation because it would take too long. Essentially, we reach at this result. So my derivative function S that essentially parameterizes my Lagrangian submanifold can locally, so if I change coordinates, it can be locally represented by one of those normal forms, depending on what the sort of critical point I have in that region. If I don't have a caustic, it's quadratic. I think then it's labeled by A1, according to this nomenclature that I have here. I mean, I didn't explain what simple and Lagrange stable means, but essentially it's a genericity argument. So I take a look at generic Lagrangian submanifolds that are stable, and then you have only these cases that survive perturbations. Yeah, and this is the main result. This is a special case because here I only have, in a general, I mean in the general Hamiltonian sense, you have two types of parameters and variables that you can, I mean, you have P and Q, and then sometimes you mix them up. I did that in my thesis. I didn't do it here because it's not really, it's conceptually it isn't anything new. It's just a change of, it's a generalization. Yes, so that's the main result. So what did we do? We classified all possible physical caustics in a Lagrangian fluid in a mathematical way. And with the help of mathematical singularity theory, we were able to find or to show that you can transform coordinates such as locally these regions look like polynomials, which is nice, they're analytic. So I get some kind of analytical representation of shell-crossing regions, which are regions that are ill-defined in our model, so I don't have any representation for them at all before doing this. From a mathematical standpoint, I didn't show this in the presentation, but what I did in my thesis was to take a look at two different classifications of singularities, the Boardman classes and the ADE classification. And, well, I developed them. And the way they are developed is very general because you only need your functions to be differentiable, and everything else, like you don't need anything else actually. Well, and I did for the real case. Usually it's done for the complex case, but that's not important. What is nice about this is that this framework is really adaptable. It can get, and it actually has been applied to a lot of fields in physics, not only cosmology. So I think the field where it was used the most was in optics, because you can describe caustics of wavefronts with that. But it can also be used, and it was used by Arnold to adapt it to oscillating integrals, for instance. And that's nice because maybe it could be applied or singularity theory could be adapted in such a way that it can be applied to integrals that resemble those that appear in KFT, for instance. And then we could maybe arrive at analytical representations of KFT asymptotics or something like that. At least that would be the hope. Yes. What could also be done is to introduce a time parameter into the normal forms I showed before. That's a bit messy because then you need a special parameter that gives you Legendre functions, but then you can really take a look at how caustics evolve in an infinitesimal way, which caustics can evolve into which ones, because not all structures can evolve into any kind of structure. Yeah, that was done a bit in the appendix of my thesis, but that wasn't part of the main work. So yeah, these are ways in which this could be expanded in the future. And yeah, this would be it from my side. Do you have any questions or remarks or yeah?
But all you actually required was the move function. Basically, you use the function.
Yeah.
So, but so what would happen if you didn't work with the standard translation to the volume motion from that? So, what would it change?
I mean, I think. Okay, the first thing that could happen is that if the equations of motions that you give me, for instance, constrain the system in some way, that these caustic conditions cannot be fulfilled, for instance, for other reasons. I think Matthias said something in his lecture regarding that under some if your system is anisotropic in some way, then for instance, you cannot have two eigenvalues vanishing at the same time for physical reasons. I mean, I've only said that mathematically it could be possible for it to happen because I haven't taken a look at my explicit potential. That's something that could happen, that you then realize, okay, maybe these conditions cannot be fulfilled for some other reasons that are not purely mathematical in nature. What cannot happen, how if you assume the same stability conditions decided, which essentially tells you that yeah, okay, it's a bit difficult to explain. But if you assume the same stability conditions decided, then you don't get more caustics. You potentially only get less if you stay in this Lagrangian picture. And I think what would be more relevant is to take a look at how does the skeleton of singularities look, right? So this pancakes that I've drawn, the fact that these edges look like this, that's Sildovich. That's a result of the way the Sildovich potential looks, of how the collapse is anisotropic and stuff like that. If you change the underlying model, then the structures you get will look different. But mathematically, nothing would change. Does that answer your question, sort of? I mean, what would change are the plots, essentially. But the mathematical reasoning behind it wouldn't. And what can happen is that some caustic cases cannot take place because for some reason, yeah, two eigenvalues cannot become singular at the same time or something like that. But yeah, it would be more constraining, but it wouldn't generalize the model more. Yeah. I didn't use that at all. The only thing that I used. But then I don't see any physical. No. the reason why I mentioned my thesis that it's Seldovich is that I use these kind of plots. And these plots are a result from the Seldovich approximation. If I use something else, then I don't get these saucer structures and stuff. I mean, the thing is, if I don't assume Seldovich and I do it in the most general way possible, that's true. What I also don't get is the factorization between the x and the time dependencies, and that I need. So this right here. One characteristic of the Seldovich approximation is that you say that your phi, the big phi, looks like this. So you have a time-dependent function, and then you have the gradient of a potential. So time and space are factorized. That allows me to essentially have isochrones of space-time. So then I can take a look at space. Space has Lagrangian structures, so I can do Lagrangian singularity theory, not worry about time, and then I can reintroduce the time dependency with the help of either you can do it in a very mathematical way with orbits in germ space, or you can do it by introducing the parameter with the help of deformations, and then you get Legendre functions. That you can only do in a framework where that factorization takes place. If my potential is time dependent, then I cannot do that. But I mean, yeah, I mean, I don't know anything about other. I mean, I'm not. I wouldn't even say. I mean, I'm not acquainted with cosmological structure formation models. But what I've used is this factorization. That was the most important part, and the fact that I have a potential at all. No. Differentiability, of course. Nice. Yeah, that's something that you said in your lecture. I didn't have time to do more about it because the thing is, for this d singularities to happen, two eigenvalues have to have the same value, namely -1, at the same time. From what I understood from the papers that I read, that is something that could happen in the Seldovich picture. But that would contradict your lecture, I think, right? If I understood you correctly. Mm-hmm. Mm-hmm. By this. Mm-hmm. Yeah.
This does not say
Yeah.
this is the
Okay.
Now the next question is if this is a then you will necessarily
Mm-hmm. Do you have, because I know, or I've read at least, and I believe them, or chose to believe them, that if you take this type of propagation, I think, then you can show that that one of the eigenvalue fields is always bigger, like that you can really order them by amplitude. So that one of the eigenvalue fields is dominates over the other ones always, but that but that they can be equal at some isolated points. So what you're saying is that if you assume a Gaussian random field, then they can never be equal, and they're always strictly ordered. So they're always, one of the eigenvalue fields is always bigger than the other ones and stuff like that. Yeah. Okay. Yeah. Okay. Yeah. So that would mean that the system gets arbitrarily close to develop one of these d caustics, but it never happens. Okay. Yeah. Okay. Yeah. Yes. Great. So there are not any further questions, then thank you. Yeah, I don't know. I hope it wasn't too far-fetched or unintelligible, or yeah. Let's see, because now I have to do like sort of the inverse of this when I present it to Johannes group. Let's see how we do on that, but yeah. No, that's actually really good because they always do their talk before going to grab something to eat. So like it's a hard limit. So at 12 they go to the Mensa. I don't think my public is going to be very happy about me not respecting that. So I think as I understood it, I only have 45 minutes with questions. I don't know. Johannes told me it's like 11 CT, and then they grab something to eat. I don't think they go to eat at 4. So yeah. Yeah. Nice.